अभी कौन तारीख 14 तारीख है now we already know a linear phase digital filter. For any linear phase filter, now a filter, analog or digital, if it is linear phase, it will always allow distortionless transmission of signal through itself. It has been discussed already in the previous class. Okay, today now we want to see, okay, the digital filters, and it will be a linear phase filter also. And we'll see how to see the characteristics of digital filter and how to design the filter. That is the most important thing for our case. So our next topic is linear phase digital filter. Okay. Now, if HN is the consider one filter, one digital filter. Okay. If for this filter, HN is the impulse sequence or impulse response. Impulse sequence or impulsive response. What is that? If we apply delta n as input, that is the impulse as input, then the output of the filter is called HN. This is unique for a given filter. Okay. So when we apply delta n, the impulse input, always for a particular filter, we will get a particular HN. Okay. So HN represents the characteristics of the filter. So it is fixed for a given filter, HN. Now, if we, for this filter, its transfer function can be found easily. How it will be there? So it will be HZ. If we take the Z transform of HN, it will be, okay, Z transform of HN. You already know Z transform. Z transform of HN. Then we can say our HZ equal to summation HN Z to the power minus N. N is varying from minus infinity to plus infinity. Okay. So that is our thing. Now, we want to find out the frequency response of the filter. Frequency response means when we vary, when we apply different frequencies as input, we'll see that the filter, the gain of the filter for some frequency will be high and for some other frequency it will be low. Gain of the filter for some frequency will be high, for some other frequency will be low. Similarly, if we apply some signal, okay, sine or cosine with a certain phase, we will find out that the output will be having another phase. It means the filter will add some phase term to the input, okay, and then the output will have a particular phase. So input phase and output phase, they are actually related by the phase characteristics of the filter. The phase characteristic of the filter is a function of its frequency, and the gain characteristics of the filter is a function of its frequency as well. Okay, so these together is called frequency response of a filter. So frequency response basically is the gain versus frequency and phase versus frequency. Okay, how they are varying with frequency. Input frequency is actually studied through this particular characteristic. Okay, now we want to investigate the frequency response of a filter or frequency characteristic of a filter, digital filter obviously. Okay, Therefore, this is obviously the steady state frequency response, because when we apply certain input frequency, initially there will be some transient at the output, but we will wait up to the steady state. When that steady state is reached, then the steady state response will be obtained. Okay, so to obtain the steady state, okay, frequency response, okay, of the filter, we put Z equal to e to the power s tau, where a is equal to j omega. Okay, when we put s equal to j omega, only the frequency characteristics will be investigated. Okay, here, okay, it is just the frequency characteristics, so sigma will be 0. You already know why we are putting sigma equal to 0 in the frequency transform, actually. Okay, just it does not contribute to anything when we want to know the frequency characteristics only. Okay, so we can write it is e to the power j omega tau. Okay, so we write it is we put z equal to s tau, it was j omega tau. So ultimately it will be a function of frequency. So h omega we are writing, just it's a function of frequency. So it is sometimes people are also writing as h of e to the power j omega, because it is a function of e to the power j omega, but finally it is a function of frequency. So I write it here as h omega. So h-o-n e to the power minus, we put z equal to e to the power j omega, so minus j n omega tau. Okay, and n is varying from minus infinity to plus infinity. So that is, from that relation we can find out the frequency response of a filter. Now, to go further, before going further, we want to see just two important properties of h omega. So properties of h omega. What is that? Our first one is the periodicity property. You see, periodicity property. We write let omega equal to p omega s plus omega dash, where where omega dash is in between 0 and omega s by 2. Obviously, omega s is the angular frequency corresponding to the sampling frequency. So we write with omega s as the sampling frequency. That is angular, obviously. So we want to see actually we are having two frequencies. One is omega, another one is omega dash, and they are related with that particular thing. It means what? Omega is some shifted version of omega dash, or omega dash is a shifted version of omega. Anyway, we can say the same thing, shifted version. Then how our h omega and h omega dash will be related to each other, that we want to investigate now. Okay. And what is p? P is an integer. P equal to 0, plus minus 1, plus minus 2. Okay, all these such things. Then what we can write? Z equal to e to the power j omega tau. We write omega, just put the value of omega here, e to the power j p omega s plus omega dash. Okay, into tau. Or we can write e to the power j p omega s tau. Okay, p omega s j p omega s tau, and plus j omega dash tau. Now, therefore, we can write it what? It is equal to e to the power jp 2 pi omega s is fs and tau means sampling period 1 by fs plus j omega dash tau. So ultimately fs and fs cancels. E to the power j 2 pi p plus j omega dash tau. Here now e to the power j 2 pi p, it is what? We can write e to the power j 2 pi p into e to the power j omega dash tau. You can write it that way. But e to the power j 2 pi p is what? Cos 2 pi p plus j sin 2 pi p. So I write it in the next page. Now, e to the power j 2 pi p means, you know, it is cos 2 pi p plus j sin 2 pi p. Now, cos 2 pi p is 1 and sin 2 pi p is 0 for any integral multiple of 2 pi. So ultimately, it is just 1. So it is what j 2 pi p. So what is j? J equal to, we can write here, from the next previous page, we can write z equal to the word j omega tau equal to, this is 1 e to the power j omega dash tau. Okay. So it is z equal to e to the power j omega tau equal to e to the power j omega dash tau. Okay. Thus, what we can write? What is our h omega? H omega equal to hz, where z equal to e to the power j omega tau. Okay. That also can be written as, it is hz. Now e to the power j omega tau means it is e to the power j omega dash tau. We put it, so it will be h of omega dash. There. So it means it is the, so ultimately what happens? Okay, it is the periodicity property. If you put p equal to, so it means that, so they are related with that way. So you can write that h omega equal to h omega dash. So we can write what? Just finally, we can write, let's write it here. Finally, h, okay, p omega, just I write it, h omega equal to h p omega dash, omega s plus omega dash equal to h omega dash. In general, we can write h p omega s plus omega dash equal to h omega dash for integer value of p. So if we write p equal to 1, what it will be? H omega dash plus omega s equal to h omega dash. So it is just the periodicity property. Periodicity property. Yeah. So that is our periodicity. Next, we want to see one more property, is symmetry property. Symmetry property. So here we put, let omega equal to p omega s minus omega dash. In previous case it was plus, now it is minus, where omega dash is in between 0 and omega s by 2. Okay. With omega s as the sampling frequency, angular obviously, and p equal to 0 plus minus 1 plus minus 2, this way it will be there. Then what is our z? Z equal to the power j omega tau, or j omega means p omega s minus omega dash tau, or e to the power j p omega s tau minus j omega dash tau. So j p 2 pi fs, tau means 1 by tau, 1 by fs minus j omega dash tau. So it is e to the power j 2 pi p minus j omega dash tau, or we can write e to the power j 2 pi p e to the power minus j omega dash tau. This is equal to 1. So e to the power minus j omega dash tau. So you can write since e to the power j 2 pi p equal to 1. Yeah. So a minus sign. So it is e to the power. So it is e to the power minus j theta actually. So this, if it is e to the power j theta, it is e to the power minus j theta. So it is the complex conjugate. So we can write it what? It will be e to the power j, okay, omega dash tau, its complex conjugate. Cap, where a cap is the, here we are using the symbol of cap. So complex conjugate, okay. So thus we can write, okay, I write it in the next page, or better, okay, I write it here. Thus, okay, h omega equal to h z, z equal to the power j omega tau, it is h z, z equal to, it is the complex conjugate, j, okay, omega dash tau cap, complex conjugate. So once we put here, we'll get h omega dash cap. So this is the complex conjugate of that one. Okay. So in the next page, I write, or I can write it here. Therefore, our h, now omega means here what? P omega s minus omega dash equal to h omega dash cap. So it is the symmetry property. Truly speaking, it is the anti-symmetry also, we can say, for the phase term and symmetry for the magnitude term. That particular property was also found in context with DFT. Okay, so if we combine the two properties, then we can draw a figure. So we can write what? I write it in the next page. So page number 3. Therefore, we can see that the mod of h omega is even in omega and even function of omega and argument of h omega. Argument means phase actually is odd in omega, odd function, because one angle is the negative of the other angle. So it is odd function. Okay. And the line of symmetry is what? It is all with respect to omega s actually. So combining okay these two properties of symmetry and periodicity. Okay, we can get a picture. It is what? Not only that, the real part of H omega is even. Again, so I write real part of H omega is even and imaginary part of H omega is odd in omega. So combining this property now we can draw এটা তো একদম ঠিক আছে ঠিক আছে so it is mod of H omega or real part of H omega. It is even. And here also argument of H omega or imaginary part of H omega. Right. So that is our particular thing and it is our omega axis. Now what is the argument part? It is not yet drawn. This is that, so better I draw it in a different color. So for argument actually it will be this. So it will be some having odd symmetry. Okay. So note that the pattern can be anything. It is, these are just the sample pattern. Don't think that the pattern will be always like that. No. But the symmetry property will be always maintained. So pattern which is drawn here is totally arbitrary. But the symmetry property is not arbitrary. It is following that particular logic which is given previously. So that is the characteristic of linear phase digital filter. Always, whatever be the type of the digital filter, whatever be the type of the digital filter. Now, once we know this digital filter, okay, okay, then our next task is what? First thing is that we will consider one application. We will consider one application where we want to investigate which range of frequencies we want to amplify or allow through the filter and which ranges of frequency to reject by the filter, Okay. So it means that the frequency characteristics of the filter will be decided first. It will be set first. So in the frequency domain, H omega versus omega, mod of H omega versus omega will be decided first. Okay. Once it is decided, then our next task is to find out the value of Hn, the impulse response function, okay, of the filter. Our next task is to decide the Hn, impulse response function of the filter, because ultimately the filter will work in the time domain. The input will undergo a convolution with Hn, Xn, Xk and Hk, or Xn and Hn will be undergoing a convolution and we get some Yn or Yk, whatever it may be. So in time domain, the convolution will run. and we can write a program. We can write a program, a C program or assembly language program, okay, that will be used to perform convolution in time domain. But the value of the HN will be selected in such a manner so as to maintain the frequency characteristics of the filter. So, what is our task? Our task is given a particular frequency response or decided a particular frequency response. We have to design the value of Hn. We have to design the value of Hn. So, designing a filter means designing the value of Hn from frequency characteristics. So, from frequency characteristics, we will design the time domain characteristics of the filter Hn, or we call Hn is also called filter coefficient. Okay, filter coefficients. The filter coefficients will be used to apply convolution with the input to get our output. So our next topic of discussion will be, that is a big topic. Now our discussion will be in that particular line for a large number of classes. Is that design of digital filter. Now there are different techniques of designing a filter, digital filter. Here in our class, we'll see only this particular technique by Fourier series method. By Fourier series method. By Fourier series method. Okay. So let's first we consider one thing. Let the digital filter be an ideal low pass. An ideal low pass filter. What do you mean by ideal? I'll tell you obviously. With a cutoff frequency of omega c, okay, then mod of h omega may be represented as mod of h omega. So I write it here. We know the gain characteristics of mod of h omega is symmetric and is periodic. Its periodicity is what? With omega s, the sampling frequency. Okay. And it is also having even symmetry. Even symmetry. So the filter characteristic will be always like that, and it will be repetitive in nature. Okay. And but when we design it, what is our usable range? In our practice, we use only this thing. This is our usable range. Okay. Some half of the sampling frequency to 0. In that region, we can use the filter in our practical application. Okay, other things will come automatically. So if we set the characteristic only this way up to that range, other characteristic will be for the other part of the frequency will be decided automatically. Clear? So thus we see that, just I write it, although I told you that h omega is found to be periodic with omega s in frequency domain. You see that periodicity we find it in which domain? Not in time domain. This is not periodic in time domain, it is periodic in frequency domain. So that's why I am writing this thing. It is very important observation. Okay. So we compare. So comparing this periodicity with that of a periodic signal, with that of a signal whose periodicity is in time domain. In time domain, complex Fourier coefficients of a periodic signal may be evaluated. What does it mean? What does it mean? If it was HT versus T, or mod of HT versus T, whatever it may be, it would be periodic in time domain. Then we can apply our Fourier series method, okay, or Fourier series, and we can express it, okay, as an infinite sum of Fourier coefficients. These Fourier coefficients are the functions of frequency. So if it is HT versus T, or Hn versus n, whatever it may be, in time domain, then we can find out what its Fourier coefficients in frequency domain. But now the case is just opposite. It is not HT versus T, it is H omega versus omega, and it is periodic in omega. So we can apply, since it is periodic, we can apply the Fourier series technique here also. And we can express it in terms of complex Fourier coefficient. But now the Fourier coefficient will not be a function of frequency, it will be a function of time. Just opposite thing, just the duality property. It will be a function of time. Okay. So what I say verbally here now will be written in the next page. So please note that concept. If you have any doubt, ask me today. That is the most important thing. If you understand this thing, other things will come following some mathematical procedure. But conceptually, this is important. I write it in the next page. I write it in the next page. So it's page number 5. Okay. So now we write for a periodic time signal xt with capital T0 as the time period, xt equal to so with T0 as the time period, we can write xt equal to summation of Fn e to the power j n omega 0 t, where n is varying from minus infinity to plus infinity, with, so it is Fn to xt conversion. Just the reverse is what? It is here frequency to time conversion. Frequency Fn to time xt conversion. And the reverse is with Fn equal to 1 by T0 integration xt e to the power minus j n omega 0 t dt 0 to capital T0. Okay, so that is the relation. You have already studied this thing in your previous semester class on signals and systems. We are simply using it here. Now, okay. Now, if we now note that we compare this periodic property, comparing this periodic property with that of a periodic signal. Okay, so that this periodic property that of a periodic signal. Okay, this with that of a periodic signal of h omega. Okay, evaluation may be carried out as h omega equal to summation hn e to the power minus jn omega tau. Okay, where n is varying from minus infinity to plus infinity. It is coming from Fourier transform, you know. A result already known, obtained. With, note that here xt and ht, they are both are periodic equivalently. With h omega is periodic like xt. So h omega is periodic in omega like xt in t. Okay, h omega is periodic in omega like xt in t. Okay, therefore what we can write, xt and h omega are equivalent in our treatment. Similarly, since ht and h omega is equivalent, then fn and hn will be equivalent. Okay, similarly fn and hn are equivalent. We can write here what is the periodicity of xt? It is capital T0. Okay, so periodicity, and here periodicity of h omega is omega s. Okay, so we can write T0 and omega s are equivalent, showing periodicity. Okay, in both the cases, T0 is the periodicity of xt and omega s is the periodicity of h omega. Okay, then there is a constant term omega 0 here, and there is a constant term minus tau. They will also be equivalent. So consequently, we can write here minus, we can write omega 0 and minus tau are equivalent. Okay, then hn may be evaluated as what? I already told you that fn and hn, they are equivalent. So we can write hn in place of fn here. So just like h omega in place of ht, hn in place of fn, here minus tau in place of minus tau in place of omega 0 and omega in place of t. Here also we can write, therefore, t and omega. So better I write it here. T and omega are equivalent. Okay, so we can write Fn and Hn, they are equivalent. So Hn equal to 1 by, in place of T0, we can write omega s. Okay, integration 0 to omega s. In place of xt, we can write h omega e to the power. Now minus omega 0 in place, we can write tau. So j n tau omega, and in place of t, we can write d omega. Okay, so impulse sequence of digital filter. Impulse sequence of digital filter. Right, impulse sequence of digital filter. Now that thing, so once we know this is a very important relation, we can write 1 by omega s. We are segregating it in two parts, 0 to omega s by 2. Plus from omega s by 2 to omega s. Okay, why we are dividing it that way? Sorry. There is one h omega also. Why we are writing it actually? It will be clear if we see our previous figure. 0 to omega s by 2. So it is the folding frequency actually. So 0 to omega s by 2 and omega s by 2 to omega s. Okay. Now omega s by 2 to omega s, this part is same as minus omega s by 2 to 0. That is the periodicity property. So this part, you see this part, minus or plus omega s by 2 to plus omega s. This part is same as that part. So it is minus omega s by 2 to 0, that part. Why? It is because of periodicity. Because of periodicity property. So we can write it, therefore, page number 6. Using periodicity property, we can write omega s by 2 to omega s, h omega e to the power j n tau omega d omega equal to minus omega s by 2 to 0, h omega e to the power j n tau omega d omega. Okay, so omega s by 2 to omega s means minus omega s by 2 to 0. Omega s by 2 to omega s means minus omega s by 2 to 0. So that relation omega s by 2 to omega s, that one, this part will be replaced by this part. So hence we can write Hn equal to, now here first part will be same, that second part will be replaced. So it is 1 by omega s, 0 to omega s by 2, h omega e to the power j n tau omega d omega plus, now that part will come, minus omega s by 2 to 0, h omega e to the power j n tau omega d omega. Or we can write 1 by omega s minus omega s by 2 to plus omega s by 2, h omega e to the power j n tau omega d omega, which is equal to hn. So this is a very important relation. So this is what? Once we know a particular frequency characteristics, so it means known frequency characteristics, characteristic of a filter, of a digital filter. It is decided, no. Now our task is to design Hn, following their relation, following the relation. So from H omega, we can get Hn, the impulse sequence. Note that H omega is our known characteristics, but we have to write a program in time domain, either in assembly language or in C, either in assembly language or in C or C++, whatever it may be, okay, to implement Hn. That will be undergoing a convolution with the stream of input signals in time domain to give our output from the filter. So once we know Hn, then only we can write a program, okay, to implement that convolution. So that is the essence of design actually. Obviously, there are some more issues now that will come one after another, but that concept you need to understand clearly. Based on this, okay, it will be the foundation of all our subsequent discussion. Okay, now I go to the next page. Page number 7. এটা আবার কি কেমিস্ট্রি কোত্থেকে এলো? ও so page number 7. Now frequency response of digital filter. Digital filter. What is that? The frequency response, we want to see something because of some more reasons. So again, we are going to the frequency response now. So frequency response H omega may be expressed as H omega equal to summation Hn e to the power minus Jn tau omega, where n is varying from minus infinity to plus infinity. Or we can write it, okay, n is varying from minus infinity to minus 1. Just we are segregating the terms. Then n equal to 0 term, we write it separately. H0 e to the power 0 for n equal to 0. E to the power 0, 1 plus summation n is 1 to plus infinity Hn e to the power minus Jn tau omega. Okay. Or now we know our summation always maintains commutative property. Okay, so we know A1 plus A2 plus A3 equal to A3 plus A2 plus A1. So summation is always maintaining commutative property. So we can interchange in the summation the lower limit and upper limit. So n is varying from minus 1 to minus infinity Hn e to the power minus Jn tau omega plus H0. Rest part is as usual. Clear? Now what we do, we write, instead of writing negative sign here, better I write negative sign. When n equal to minus 1, it will be h minus 1. It will be e to the power plus J1 tau omega. When n equal to minus 2, it will be h of minus 2. E to the power minus of j minus. So e to the power plus J2 tau omega. So there will be a change in sign when we put the value of n, negative values of n. So instead of doing that thing, we can do the same thing another way. We write h minus n here, then n will be varying from 1 to infinity, and e to the power Jn tau omega, no negative sign here anymore, plus H0 plus n is varying from 1 to infinity, hn e to the power minus jn tau omega. You can write it. Now, if our filter, if hn be real and symmetric, don't think that it will be always. We want this particular thing. That is what? H minus n equal to hn. So what it will be there? If we plot it, it will be, say, H0 is n. Say some h1 is here, h1 for n equal to 1. Then h minus, h minus 1 is here. Then h2. Then it will be, thank you. Just I forgot it. H minus 2. Similarly, you can write something like, say it is h3. So it is h3. So it will be, it is minus 3. So it is h minus 3. So this way. So it is symmetric actually. Again, say it is 4. It is h4. In that case, it will be h minus 4. So it is symmetric. Okay, so it will go in both ways. In that, it will look something like this. Then what happens? We can write hn. Then we can write hn here. Then h omega equal to, I write h0 here, plus here this part is hn e to the power jn tau omega plus summation hn e to the power minus jn tau omega. Or we can write h0 plus, we take summation sign common, 1 to infinity hn e to the power jn tau omega plus e to the power minus jn tau omega. Clear? We can write it that way. So e to the power j theta plus e to the power minus j theta means it is 2 cos theta, 2 cos. So I write it in the next page. Okay, I write it in the next page. Page number 8. So therefore our h omega is equal to h0 plus 2 summation hn cos n tau omega, where n is varying from 1 to infinity. Okay, so this is a real quantity. It means what? Okay, so when hn is real and symmetric, when hn is real and symmetric, our h omega becomes a real quantity. There is, see, there is no j term in the frequency response. Okay, so what is this phase shift? Phase is 0. 0 phase means there is no j, means 0 phase. So for all the input frequency omega, okay, the it will be a linear phase filter, because for a linear phase filter we know it is delayed by some phase characteristic will be some omega into td. Omega into td, td is a time delay. That is a linear phase characteristics. But when time delay td is 0, then what happens? The phase term will be 0. Phase term will be 0. So even a linear phase filter can have a 0 phase. A 0 phase means it will be, okay, input signal will easily pass through the filter, digital filter, to its output side, okay, without any distortion. So thus, so you can say that, thus, with a real and symmetric hn, a real frequency response may be obtained. this results in a distortionless filter with zero phase shift. A linear phase filter, as a matter of fact. Okay. So from H omega, we can find out. So from Hn, we can find out if Hn is real and symmetric. We can find out H omega. Okay. Note that we have not proceeded to the design part till now. The design part will be just the opposite. Here H omega will be known, and accordingly we can find out Hn. Just the opposite process. It is not yet initiated. Obviously, it will be done in our class later. Okay. But now you see, for this particular filter, there is a realization problem. We cannot realize this filter in practice. We cannot implement it in practice. Why? We'll see this thing. So next part is realization problem. Okay. So first we start with, to investigate the realization problem, we start with Hz equal to summation Hn z to the power minus n, where n is varying from minus infinity to plus infinity. So in terms of input and output, what we get? Say this is our Hz, our Xz is the Z transform of input, and Yz is the Z transform of output, and Hz is the Z transform of impulse sequence. And that is our digital filter. Okay. So in terms of input and output, we can say our Hz is Yz by Xz, Z transform of output by Z transform of input, and it is equal to what? This one, summation Hn z to the power minus n, n varying from minus infinity to plus infinity. Now what we do? We just apply cross multiplication. So it will be Yz equal to, so we can write it, okay, Xz summation Hn z to the power minus n. That one. Or we can write Yz equal to summation Hn. We take Xz inside, z to the power minus n into Xz. Clear? Now note one more thing. So we want to investigate this z to the power minus n into Xz. I write it in the next page, page number 9. Where it is? Now we know Z transform of xk, we are not using n is used, okay, separately. Z transform of xk is xz, okay, where Z transform of xk is what? Summation of xk z to the power minus k. It is minus infinity to plus infinity. Then applying time delay property. You already know the time delay property. Okay. We can get Z transform of X K minus N is what? It is Z to the power minus N into XZ. So, but this is equal to what? It is summation X K minus N Z to the power minus Z to the power minus K, where K is varying from minus infinity to plus infinity. That is equal to just time delay property. Just K is replaced by here K minus N. Okay. Then we can write it Z to the power minus N, okay, into XZ. The signal is time delayed. Yeah. So Z to the power minus N into XZ now can be replaced by this particular thing. Okay, in the previous expression. So here we are getting Z to the power minus N into XZ. So now we will replace this with that newly obtained expression. So YZ equal to summation HN. Okay. Therefore, we get our YZ equal to summation HN, N varying from minus infinity to plus infinity. Now that is replaced. We write it X K minus N Z to the power minus K. K is varying from minus infinity to plus infinity. Okay. So we change the order of summation. Changing the order of summation, what we get? Our YZ equal to, we just take this K outside. Okay. Then we can write it that summation sign is taken inside. HN, okay. Here N is varying from minus infinity to plus infinity. X K minus N, okay, into Z to the power minus K. Okay. So now YZ may be expressed as what? YZ is the Z transform YK. Or we can write it summation YK Z to the power minus K. K is varying from minus infinity to plus infinity. Okay. Where if we compare this with that, what we get? Where YK equal to summation HNX K minus N, where N is varying from minus infinity to plus infinity. This one for K equal to 0, 1, 2, anything. So in a filter, what we get? Say this is our HN, this is our XK, and that is our YK. This is our digital filter. Or you can write HK also. So it will be YK is the, it is the convolution. So this term, it is called what? It is the discrete convolution summation. Discrete convolution summation. Okay. I want to stop today with this particular thing. But before that, any query? Anything required? No. আচ্ছা, আমাদের নেক্সট ক্লাসটা যেন কবে? এখন তো বোধহয় কি একটা চেঞ্জ হয়ে গেছে না? কালকে আছে নাকি, না কবে? ঠিক আছে, আমি দেখে নেবো, আমার মনে আছে। ওকে।